Okay, so hello, my name is Vitaliy Grudtsov. I'm from Scientific Manufacturing Complex Technological Center, and I'm presenting the work optimization of ISFET structure formation technology for use in biochemical analysis systems. So modern biochemical analysis systems widely used in such areas as environmental monitoring, medicine security, and so on. They are generally constructed as follows. So first, we have an analyte delivery system, which brings the analyte or the substance of interest to the sensing layer. This can be either a gas delivery system or microfluidics and so on. Next, we have a sensing layer, the point of which is to interact with the molecule of interest in such a way that can be picked up then by a single transducer and then turned into electric signal. This sensing layer can be many things such as DNA, subtomias, whole cells, and so on. Then we have a signal transducer, which converts this interaction to electrical signal. And then this signal is passed down to integrated circuits for this processing. So one of the most popular devices for that is used as single transducer is ion-sensitive field effect transistor, or ISFET. So ISFET is basically MOSFET transistor structure with metal gates replaced with the electrolyte solution. So any changes in pH values or ion exchange in the solution or specific absorption on surface of ISFET leads to a change of surface electric potential. Then in turn, it changes the conductivity of the channel, and then we have an electric signal. So you can also modify the electric layer to have with something like DNA or aptomia to have sensing layer on top of the ISFET structure. So you have both the sensitive layer and the signal transducer in one circuit element. And the main thing that makes ISFET popular that it is compatible with CMOS technology. So it can be integrated into production of integrated schemes. So naturally, all this makes ISFET research very promising. So in this work, we propose formation of such a transistor with in modification called extended gate, in which the sensitive surface, which is directly in contact with electrolyte, is moved outside the transistor body, and the connection between them carried out using a so-called floating gate. So it has such a design has several advantages, such as it can be integrated to CMOS technology with some post-build treatments or finishing operations. It can, in the case of having several layers of metallization, it can bring the sensitive surface above the single processing circuit and thus save the area of the entire crystal. And then in the technological route that I'm about to show, you can have control of the sensitive surface parameters. So we have topology of the transistor on the slide. It can be broken down to three main parts, which is the standard MOSFET structure, which is also shown at the bottom of the slide, with the polysilicon gate. Then the signal line, which in which polysilicon is crosses over into metal, in this case aluminum, and then the sensitive surface area itself, and it is this part that implies additional finishing operation. So let's take a look at the technological route. So the top of the slide is a stack of silicon insulation, silicon oxide, aluminum, and silicon oxide, silicon nitride passivation before any of the finishing operations. Then, after plasma etching of the passivation, we have argon stripping of the top part of the aluminum layer, and then annealing of this aluminum layer to form aluminum oxide. And then we have formation of sensitive surface, in this case, tantalum oxide. So let's take a closer look at each of these operations. So the stripping and annealing is necessary in our experience because we found the sensor characteristic of the final device very strongly dependent on the surface between the floating gate and the sensitive surface dielectric. This will be shown later when we get to the current voltage characteristics of the device. So the preparation for the sensitive surface deposition is carried out in two steps. First, but they into one unit, apex SLR unit, and in one waveform cycle. So first we have argon stripping of the first part of the aluminum layer of the top part. And then in the same chamber, in the oxygen atmosphere, we have low temperature thermal oxidation of the aluminum layer, forming a thin film of aluminum oxide. And only then we have atomic layer deposition of sensitive surface, in this case tantalum oxide, which has chemical stability in water solutions and has the possibility of creating structures with poles attached to swing. So aluminum layer deposition method can lead to creation of very uniform films with a control thickness, which is what's needed. So LD deposition was done on FGG2 unit using Kentucky's dimethylamine tantalum precursor using a thermal process at 250 degrees Celsius and DNase H2O as oxygen source. This film was later characterized using ellipsometry and secondary ion mass spectrometry. So ellipsometry gives us thickness of the film, which is was as intended was 50 nanometers, so very thin layer, and non-uniformity across the test wafer was less than 2%, which is very good. And the secondary ion mass spectrometry, we mainly confirmed that the sensitive surface is, in fact, tantalum pentoxide and not another stereochromatic composition. And we also confirmed that yes, in fact, we have an aluminum oxide layer underneath the sensitive surface. Secondary ion mass spectrometry also yielded some tantalum nitride peaks, which could be indicative of precursor elements inside the oxides. But as we will see later, this did not have an effect on the characteristics of the transistor that were of interest to us. But this information can be further used in optimizing the ALD process. So this is the measurement scheme of ISFET transistor. This was done on a probe station using GLMP 1500A parameter analyzer on a sample chip, and electrolyte was on top of this chip inside the well-like structure, which was formed on the surface of the chip using direct lighting method. The measurements were done in the subthreshold region because measurement in this region is more sensitive to changes in surface potential than measurement in strong inversion region. So the main characteristics of interest to us are hysteresis and subthreshold swing, which should not be worse than original structure. So here we have current voltage characteristics of the obtained device with the semi-logarithmic scale on y-axis, and on the left we have the process without against treatment and annealing step. And as you can see, both the subthreshold swing is worse than the original structure with aluminum oxide. And more importantly, hysteresis is very large compared to the original structure. And on the right, we have the optimized process, which optimized three-step process. So the aluminum surface preparation step also introduces some hysteresis into the structure, but it is cleared when the sensitive surface deposition is carried out. So the finished structure has very low hysteresis value, which is which has a lot of influence on the stability of the sensor characteristics. And so we shown. So to demonstrate it, we have done a pH dependence curve. So as the pH value of the gate electrolyte is changed, so the current voltage curves of the device shift alongside voltage axis. And so if you can, if you record current voltage curves at each point of the pH value and then compare it, compare the voltage shift between them, you can have pH dependence. So there's actually two curves here. The forward curve, which was obtained when changing pH values from low to high, from 3 to 7.4, using the same buffers, citrate phosphate buffer. And then the reverse line, which was obtained by changing the pH values from high to low. And they are extremely similar and they conform to each other, which is a direct consequence of having a low hysteresis of the structure and of the chemical stability of the tantalum pentoxide. So, in conclusion, we an ISFET transistor in which the sensitive surface directly in contact with electrolytic solution is moved outside the transistor body was developed. We proposed the method of surface preparation, which significantly decreases the hysteresis and which subsequently has a huge impact on the stability and repeatability of biosensor index. So some future work in this direction can include development to adapt the method for other sensitive surface materials. Well, basically, you just change one step, the step of LD deposition to the material you're choosing, and which should depend on the final device. And then we can develop a microfluidic system for the device, for the delivery of the analyte device, which brings us closer to creating the whole system, from the analyte delivery system down to the signal processor. So thank you for your attention.